Hello and welcome back. I'm Matthew Lay, and today we're going to study Ohm's law, which is the study of resistance, and we're going to explain what a resistance is in a electrical circuit. So we have some objectives here. First, we want to list the three basic electrical measurements. We've already studied two, voltage and current. So we want to define electrical voltage, or in our case, redefine electrical voltage. And we're going to learn that that is analogous to electrical pressure. And we want to define or redefine electrical current, which is electric flow. And we want to define electrical resistance, which is like a restriction to the flow of electrons in a circuit. And then we want to be able to calculate a third measurement given any one of those other two. So we have volts, amps, and we're going to learn the measurement for resistance. But if we have any two of those, we can calculate the third. Okay. Let's review voltage here. So a voltage, we used in a previous slide an example of it being like a water tank. Well, it could also be viewed of like a balloon, that you blow up a balloon and it has a potential pressure inside of it that if we release the air out of the balloon, we can do something with. But we have a potential difference in a battery. Comparing it to the balloon, the difference in pressure would be the pressure inside the balloon compared to the pressure outside the balloon. In a battery, it's the difference between the positive terminal and the negative terminal, and we call that the potential difference. The potential of this particular D-cell battery is 1.5 volts. The potential difference of a 9-volt battery would be 9 volts. So that is the potential difference that we have between the two. And when we talk about that difference, it's between the positive and the negative terminals on that battery. Okay, so that is our voltage. We can also think of it like a pump that is in a water system. Now, a pump is the driver of pumping water, so you can't have flow without the pump, and subsequently, you can't have electrical flow without voltage. You have to have some voltage source before you can actually get your electrons to move. So let's talk about electron movement or current. So I put this battery into a very simple circuit, and we know that we have a potential difference here. At the top, we have a positive terminal, and at the bottom here we have a negative terminal. And over here, I have a small version of our atom, and we have a number of protons, neutrons, and electrons. And if it's stable, we have the same amount. And if this is a copper wire, we're going to say it's copper. We have 29 protons and 29 electrons because they're stable. So I'm going to depict those with these red dots. If you notice, the neutron over here is red in color, so that's why I picked red for the spheres. And that means a red circle is going to depict a copper atom that has 29 protons and 29 electrons. So we call that a stable atom. Now we know that we have a potential difference here, a potential charge. This end of the battery is going to be more positively charged. This end of the battery is going to be more negatively charged. And we know that copper, from our previous study, is a very good conductor. And the reason it's a very good conductor is it has one electron in its valence ring. And because it only has one, it'll freely give that up. So this neighboring atom right here is going to easily give up and add a electron into the top of our battery. And so there I'm just denoting that our red dots depict our neutral atoms. But now you notice that sphere turned blue, and it turned blue because over here I'm showing protons as being blue in color. And it turned blue because an electron actually moved out of that atom and was attracted into the positive terminal of the battery. It did that because opposites attract. That is one of our findings from Charles Coulomb. And when that atom or that electron was removed from that copper atom, this went to a net positive charge. And you notice over here protons are blue in color, so I turn the sphere a blue color, meaning that we have 29 protons but only 28 electrons. That means that we are a net positive in charge. More positive protons than negative electrons means that we have a positively charged atom. Okay. Now this is not you're not going to stop right here. This atom right here will also want to freely give up its electron to this guy. So it will pull an electron from that atom over to this atom. And I'm explaining there that the blue means that we are a net positive. So then it happens again. The neighboring atom there gives up its electron, and this atom turns blue because the electron was attracted to the neighboring atom, and this process keeps happening. The chain reaction happens all the way down the line. The electron from here got pulled over to this one because it wanted to be stable, and it's a chain reaction. Okay. So one way to describe how we are depicting this in this movement that I'm showing with this blue circle, if you notice this blue sphere is moving from this positive of the battery to the negative of the battery. Okay. And some people call that hole flow, meaning there is a hole in this atom because it has 28 electrons, but it has 29 protons. And so the hole or the missing electron is moving this way. Okay. But as we know, the electrons, and notice over here, electrons are black in color, and that's why the arrow here is black, the arrow here is blue, because the positive charged atom is moving this way, but the negative electrons are moving that way. And this is how different physicists and some people in the electrical field can differ on describing the flow of current. So the flow can be described as going from negative to positive or from positive to negative. It depends on what you're trying to describe. Are you trying to describe the atom, the holes, the ones that are positive, which direction they are moving, or are you trying to describe the electrons in which way that they are moving? And this is a debate that goes all the way back to the beginning of electricity. And we've talked about the System International unit or the metric system, and we have talked about the volt and the ampere as measurements for voltage and for current. Well, they go to these conventions. Even back then they had conventions, and there was this debate over which way current was flowing. And at a convention, the scientists got together and they voted on which direction they should officially say the current is flowing. And the decision was made that it was this whole flow, but they didn't like that name. And since they were at a convention, they decided to call it conventional current. So when you describe current flowing from the positive of the circuit to the negative of the circuit, that is called conventional current. If you talk about current flowing from the negative of the battery to the positive of the battery, you're talking about the electron movement, and that is described as electron current flow. Okay, so in this class, moving forward, we're going to focus on what you're going to most likely hear in the field, and that is conventional current flow. So moving forward, we're going to talk about current flowing from the positive of the battery to the negative of the battery, or conventional current flow. So I'm depicting that here with these arrows. Viewing current flowing from the positive to the negative will be considered conventional current flow. And so and physically, it'll make a lot more sense when we get into more electrical symbols. The electrical symbols, which came about at these conventions as well, use arrows quite often to show where the current is flowing, and the arrows are pointing in the direction of conventional current flow. Fluke meters put arrows on the amp clamps, and that amp clamp is pointing in the direction of conventional current flow. So there's a lot of reasons that I have to study that. But the main thing is when you're out in the field, people are always going to be talking about current going from the positive to the negative terminal of the battery. Okay? So again, we have our pump, the battery, that is pumping electrons into the system. Okay, so it's actually technically in the battery, it's pumping them from the positive to the negative of the battery because it's pulling the electrons out of the copper wire on the top in this circuit, and they're flowing out of the bottom. But because the holes are moving from the positive to the negative, we're going to call that conventional current flow, and we're going to always talk about positive to negative flow. Okay, you can think of using the pump analogy. The pump here that I'm depicting is the battery. The flow is the water that would be coming out of a hose that would be connected to that pump, and that flow that is moving through the wire is our definition of electricity. So the flow of electricity through a circuit is termed electrical current and is measured in amperes. We always call it amps for short, and we abbreviate that with the letter A. That's a review from a previous session. And we also use the letter I. Remember, I is intensity. When you get shocked, hopefully no one will get shocked, but if you've ever been shocked in the past, you have felt a very intense feeling. You're actually feeling the current flowing through your body, and it's an intense feeling. So that's how I remember that I represents the electrical current in math formulas. Okay, so we have a thought experiment here. If I take that circuit that I had on the previous slide and I add more bulbs, will it have an effect on my electrical current flow? And if you want to pause the video, you can, and think about that and come back. We're going to dive into that and see if we can solve that thought experiment. Okay, so we're going to come back to that in a minute, but we want to talk about a concept. We have another scientist here that we want to look at. His name is Georg Ohm. He was a German physicist in the early 1800s. So all this is happening about the same time. Remember, it was the late 1700s that we talked about Volta and him creating the battery. Ohm found that voltage and current were directly proportional to one another, and we're going to look at this on a chart. And his findings became known as Ohm's law. So this is actually a picture of him, and he does look German. He doesn't look very happy. But here's him doing an experiment. Now this is kind of a neat little experiment that he's doing. So even though Alessandro Volta had created the voltaic pile, or the first battery, it wasn't widely available. So what he's doing here, he's using a little device called the Seebeck effect. And what the Seebeck effect is a little battery of its own. He has a little pot here full of ice. And then he has a kettle here full of hot water, and he has a piece of metal that is dissimilar to copper in between the two, and he's pouring hot water in one, which excites the electrons in the metal, and he has the water, the chilled water, the ice in the bath in the other end, which tames the electrons, and it causes this electrical current to flow from the hot to the cold. And he's creating a little battery with that. And then he has these lines of copper that he is adjusting the thickness of the metal and the length of the metal and those sorts of things and doing experiments. This is a very simple ammeter that he's using to measure the current. And we'll talk more about that in future lessons. Okay. Because of this experiment that he was doing and all the data that he was recording, and he later found this phenomenon called resistance, the System International unit for resistance was named in his honor. And so resistance will be measured in ohms after his last name. Okay, so resistance, his experiment was basically changing the thickness or the length of the wire. So if ohm kept the voltage the same, but he increased the wire length, the current that he was measuring went down, it decreased. But if he kept the voltage the same and made the wire shorter, decreased that length of the wire, the current increased. So he tried to understand why this was. So then he kept the wire length the same, and he made his battery stronger, that little Seebeck effect that I described on the previous slide. He increased the voltage, and the current went up. And conversely, when he still kept the wire length the same, but he decreased the voltage, the current went down. And he started to build an understanding of the relationship, the correlation between voltage and current, and he came up with the concept of resistance. So he determined that the restriction to flow of electricity through the circuit could be calculated just by using the voltage and the current. And the resultant of that calculation was termed electrical resistance. Okay, so we have resistance in everything. The copper is no exception. So a small short copper wire has more or less electrical resistance in it than one that is same diameter but much longer. And that makes sense that you want the wires for like jump starting a car from car to car not to be 100-foot wires, because you're going to lose voltage. There's going to be a voltage drop in that wire if they're pretty long. That's why most of them are 6, 8, 10 feet long, just to keep any voltage drop from occurring. The resistance to the opposition of resistance, simply defined, is the opposition to the flow of electrical current. Okay, so that's going to be a good thing to denote. That's going to probably be a test question. Resistance, we're going to use the letter R to represent it, so that one's a little easier to remember. Remember, E is for voltage, E, electromotive force or voltage, and I for the intensity that you feel with current I is for current. R is for resistance. That one's a lot easier to remember. And the unit for resistance is named after Georg Ohm. I don't think I said his first name, but it's not George. It has no E at the end. It's Georg Ohm, the ohm, and is symbolized by the Greek letter omega, which is that upside down horseshoe looking symbol. So here is what we term Ohm's triangle. And remember, E for voltage, I for current, and R for resistance. And this is a simple table depicting what I was describing on the previous slide. If voltage went up, that's what the up arrow means, and the resistance in the wire, the length of the wire was kept the same, the current went up. If voltage went down and the length of the wire was kept the same, the current went down. But if the voltage was kept the same and the length of the wire went up, the current went down. And if the voltage stayed the same and the length of the wire was decreased, the current went up. Okay, that gave us these two relationships. Now, if you're not used to seeing this little symbol, that means proportional to. Okay? And what that I with that funny symbol E means is I is directly proportional to voltage. So if the current goes up, the voltage goes up, or if the voltage goes up, the current goes up. We can see that here. We've got two arrows pointing up, 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 or down, down. And here, remember the term for this from our math functions presentation? This is inverse, inverting a number, so it's putting 1 over that number. And this means that current is inversely proportional to resistance. So that means if resistance goes up, current goes down. If resistance goes down, current goes up. Okay, so that's what that means. Okay, so that is one way to describe it. It's a little bit easier just to look at this triangle to understand it. So this vertical bar here means we're going to multiply across, and this horizontal bar here, just like in a fraction, means we're going to divide across here. So if you take your, imagine that I am covering up the eye here with this cursor. So you would cover it up with your thumb. You could do that on the screen. Just cover it up with your thumb. And you see, then we'd be solving for I, whatever we're covering up. And I is going to equal E divided by R, because this E is over this bar, or divided by R. Okay? And that's where this formula comes from. I equals E divided by R. So here, we're solving for E. So right where my cursor is with the red circle, take your thumb and just cover that up with cover the screen up with your thumb, the E, and you'll only have I and R showing. Well, I, if it goes across a vertical bar like this, that means multiplication. I times R is going to equal E. That's where we get the formula here. And so here, if right where the cursor is, cover that up with your thumb, and then you're left with E over I. So E over I, E divided by I, is going to be our formula to calculate resistance. Okay, so that's our Ohm's triangle, and I will hand out a information sheet that will have this on there for you that you can use in the future. Okay, so let's go back to our thought experiment. We know that this relationship here, if resistance goes up, our current's going to go down, or if our resistance goes down, our current's going to go up. So we're going to come back here. Are we adding resistance into this? Well, yes, we are, because we're slowing down the current because we're adding more load here. We're adding more light bulbs. Okay. So yes, adding more light bulbs will increase resistance in the circuit. When we increase resistance, we are going to have an effect on current flow, and in fact, the current flow will go down. Okay, so we're going to look at that mathematically here. So we're going to use our Ohm's triangle, and our battery is going to be our E, that's our voltage, and all of our light bulbs together is going to be our resistance, or the R in our equation, and I equals E divided by R. And if you notice, if R goes up, that means the denominator is going to be bigger. And if the voltage is kept the same and our denominator gets bigger, that means our current's going to go down. 1/2 is a bigger number than 1/4. The 4 is a larger number in the denominator. And so we will have less current flowing in this. So increasing the load, the number of light bulbs, increases the resistance. I equals E over R. Higher resistance equals lower current. Okay, let's review. List the 3 basic types of electrical measurements. So if you want to pause the video, think about those and then come back. Okay, we have voltage, current, and resistance. We're actually going to have another measurement that we're going to study in a future lesson, but currently those are the three that we have studied so far and the three that we're going to use most often. Define electrical voltage. Okay, again, pause, think to yourself, and then come back. Voltage is the potential difference in charge between 2 points in an electrical circuit. So we've talked about a battery, but technically in this circuit back here, there is a potential difference across this light bulb. You could measure a voltage drop. We're going to learn more about voltage drop in a future lesson. But you could measure voltage here, and there's going to be a potential difference. There's going to be more voltage here than there is here because we've lost a certain amount of volts that's dropped in that light bulb. Okay. Define electrical current. Again, pause and then come back. Electrical current is the flow of electrons in an electrical circuit. Remember, electricity gets its name from the movement of electrons. Okay, so electrons means electricity. But now we know that we're going to discuss from now on conventional current flow, and we're going to talk about flow going from the positive to the negative of the battery. Define electrical resistance. This is our new concept that we actually learned about in this lesson. So again, pause and then come back. Electrical resistance is the opposition to the flow of current. Okay, so anything that causes the flow of current, we've only talked really about the length of the wire, but there are other components. We physically make a component called a resistor, and it's designed to have a specific resistance, and its internal workings have more opposition if it has a higher resistance than if it has a lower resistance. And finally, calculate the resistance of a circuit that has a 9-volt battery that is supplying 3 amps of current. So if you want to pause and do the calculation. Okay, coming back, we're going to use our Ohm's triangle here, and we're trying to solve for R, so you can cover up the R with your thumb here where I have the cursor right now and get your formula. Our formula would be E divided by I. E is 9 volts, I is 3 amps, so we're going to take 9 volts and divide it by 3 amps, and we'll get 3 ohms. Okay, so E equals R equals E divided by I. E is the 9 volts, I is the 3 amps, so R is going to be 9 divided by 3, or 3 ohms, which is our unit for electrical resistance. This concludes our lesson on Ohm's law and electrical resistance. I hope that was helpful, and we'll see you in the next lesson.